from where I've been. So I grew up in Dunedin, went to Otago Uni for undergrad, and then I went over to near New York in New Jersey to do my PhD in study of fusion energy. So this is like how you contain the sun in a bottle, basically, to make power in the same way as the sun. And if we made it work, we would have limitless clean power, which would be fantastic, but it's really difficult, and so people are still working on this. But during my PhD, I got kind of more interested in the astro sides of things and did my PhD on more astrophysics. So then I went to California, to Caltech. This is a picture of the Caltech astronomy building, and they have the Palomar Observatory, which has some really impressive things, including the ZTF, Zwicky Transient Factory, and other things that I see that some of you guys are involved in. Was there for 2 or 3 years, came back in a complicated route because we realized that Dunedin's a pretty nice place to live, wanted to come back here. So now I'm a research fellow at Otago, and I do a little bit of teaching, like 1 course, or 1.5 courses, and mostly research into various astro things. So if all these subjects like the fusion and then astro and other stuff seemed kind of random, the connection between them is plasmas. So I would also classify myself as a plasma physicist. So this is just when you heat up gas enough, atoms break up into electrons and ions, and these behave quite differently because they interact with electromagnetic fields. And like 99% of matter in the universe is plasma. So if we want to learn about the dynamics of gas and magnetic fields for astronomy, then you have to study plasma. So that's kind of what I do now. So I study some stuff related to black holes, particularly the gas going around them. I'll explain that a bit more. Some stuff to do with planet formation, which is a little different, kind of a side interest. And then most recently, I've actually been working mostly on the solar wind and the corona, so the hot outer layers of the sun, and how that blows off past Earth. But yeah, kind of a random collection of topics. Anyway, so to black holes. So the first question is probably, what is a black hole? Make sure we're all on the same page for that. So I kind of like explaining it with this picture, primarily because it's a cool story. This is a picture from the early days of US nuclear tests, when they were just figuring out how to make nuclear bombs. And then there was the test ban treaty in the mid-50s, the atmospheric test ban treaty, where they said, no, now we can't explode these things above ground, which was obviously a good thing. And so they started doing underground tests. And so they got pretty good at this eventually. But the first couple, they didn't really know what they were doing. And the second one, they decided to dig a big tunnel and then weld this enormous manhole cover on the top of it. So this was like this 900 kilo lump of metal, basically, that they welded on top. And the scientists were like, well, that's not really going to work. It's not going to contain the blast at all. And then it didn't. But they had this camera, which was ultra high speed thing, taking frame every millisecond or microsecond or something. And in the frame of the camera, they caught one picture of this manhole cover flying out into space. And from this, they were able to work out that the speed of this thing was about 60 kilometers a second coming off from this nuclear blast. So the reason I bring this up is to talk about escape velocity. So if I throw something up in the air, I can't really see, so it'd be hard to catch. But the harder I throw it, the higher it goes, obviously. If I throw it fast enough, eventually you'll escape the Earth's gravity and fly off into space, right? And for Earth, that speed is 11 kilometers a second. So the manhole cover here was in principle going fast enough to escape the Earth's gravity and just fly off through the solar system, in which case it's still going. There'd be nothing to stop it. And also kind of cool, it would be the first thing to reach space, the first man-made object to reach space, because this was actually before the Sputnik and the Russians got to space. That was like 2 years later. So it's actually, as a kind of downer on the story, it's likely that this didn't happen because the manhole cover probably melted from the pressure of the atmosphere as it went through at 60 kilometers a second. But if it didn't, it will be flying around space. Or maybe there's a little remnant of it somewhere. Anyway, to go back to black holes. So 11 kilometers a second, if you jump off the surface of the Earth, you'll reach outer space. The escape velocity is such that if I squeeze the same amount of mass into a smaller volume, then the escape velocity goes up as the radius I squish it in, so the size of this thing, to the square root power, 1 over that. So if I make it 4 times smaller, then the escape velocity goes up by a factor of 2, in other words. So we go to 22. If I squish the Earth down 4 times again, you get to 44 kilometers a second. We keep doing that for a long time, down a lot. Eventually, you'll get to escape velocity of 300,000 kilometers a second, which is important because that's the speed of light. So if I squish the Earth enough, the escape velocity is faster than the speed of light. You actually have to squish it smaller than a golf ball for this to happen. But if you do this, it will turn into a black hole. And that's because Einstein tells us nothing can go faster than the speed of light. I'll come back to that in a moment. Another object you might be familiar with is the sun. If you squish the sun down enough so that its escape velocity is faster than the speed of light, it would kind of fit in pretty comfortably inside Dunedin. So we're talking about insane amounts of matter squished into a very, very small space, basically. So I guess a poll question for you guys. So the question is, what would happen to the Earth if the sun suddenly became a black hole? And the first answer would be the Earth is sucked inwards, in which case obviously we all die. The second would be the Earth stays on the same orbit, it doesn't really change, it just keeps going around, but then obviously the sun's gone out, so that would suck. So who thinks it's number 1? Who thinks it's number 2? I'm in a pretty good audience here. Exactly, number 2, because the gravity outside the object, it doesn't actually care about how big the object is. And so if you squish everything down, the thing out here doesn't know. So in principle, we would stay on exactly the same orbit. We wouldn't even notice aside from the light coming from it. So why c? So why 300,000 kilometers a second? We use the symbol c for those of you who remember your physics classes. So this is Einstein, as you probably know. And in 1905, he came up with the special theory of relativity, one of 3 papers that kind of really changed physics in 1 year from Einstein. And in the special theory of relativity, he says that c is the cosmic speed limit. So you can't go any faster than c. Nothing can. And so basically that's why this is so important for the escape velocity. If you squish this thing down enough so that you have to go faster than c, then nothing can go faster than c, so nothing can escape. In 1907 to 1915, he generalized this to what we now call the general theory of relativity. So the amazing thing is Einstein came up with all this by just thinking, basically. He sat down at his desk and he came up with thought experiments like, you know, if I'm going on a train at near the speed of light and I watch another train, what happens? Like, what does it look like? He came up with these equations by doing that. So this is the curvature of space, and this is stuff, matter and energy. And so this says that gravity is the curvature of space, basically. And amazingly, 100 years later, these equations are still unchanged. So it must be one of the most amazing achievements in science. Einstein sits down, thinks about it, writes down some equations, predicts some crazy things that no one would have ever expected, like black holes. And then 100 years later, we've measured all of the properties that he predicted and haven't found any corrections to it yet. So to me, this is just totally nuts that this is even possible. So the other amusing thing is that Einstein himself thought that he would never find a solution to these equations. So the way I've written them here, they look quite simple, but it hides quite a lot of complexity. There's some pretty complicated stuff on the left-hand side there. But then 1 year later, this guy here, Karl Schwarzschild, he found a solution, an exact solution to these equations. And moreover, he did it while on the Eastern Front of the First World War and while he was dying from an autoimmune disease. So he died 1 year later, apparently very concerned about the solution he found. So his solution had a singularity, and that's why he was so concerned, because it said either this general relativity thing is wrong or space itself has a singularity. And he didn't like the idea that either of these 2 things were true. But it turned out that the latter was true. Einstein was right, and space itself has a singularity.
You should explain what singularity is.
Yeah, I'm going to kind of come to that. I mean, we don't know, but So actually it took like 50 years. So Schwarzschild wrote down the solution, which is, we call the metric. But it took like 50 years before people even understood what the solution actually meant. Like they could see through the maths to figure out what it would look like physically. And so this guy here was Roger Penrose. He won the Nobel Prize last year for doing some really important work in this. So one of the key features of this is, of the solution. So this is like, think of it as the surface. So if you're squishing down your object, eventually it gets small enough to require going faster than the speed of light to escape. The event horizon is like that surface from which you can't escape. So anything that goes within the event horizon can never come out. And what was that it necessarily falls inwards and forms a singularity within general relativity. So the singularity here is just basically something where physics breaks down. We don't know what happens. Everything goes to infinity and things look nasty. So should also point out that actually this is like the singularity itself is at least one thing in physics that we know that modern physics cannot describe, because it's something to do with a mixture of general relativity and quantum mechanics, and it's not describable by our current physical theories. So this is a still from Interstellar, the movie that is, and it's when he falls into the black hole. Hopefully I don't ruin that for people. But he does some things with strings and stuff. So in principle, I guess my point is we don't actually know this isn't what happens in a black hole, because we don't have any physical theory for what happens in that singularity in the center. It's pretty unlikely that this is what happens. But also to point out, if you haven't seen Interstellar, definitely worth watching, because all the images of black holes and all the crazy time dilation stuff that happens, that's actually all based on real physics. And they had Kip Thorne, who won a Nobel Prize in 2017, advise them on the science of it. So it's all realistic, even though it seems totally crazy. So it's definitely worth watching, or watching again if you've already seen it. So one more little part about the history of this. Roy Kerr played a really integral part of this, and he's a New Zealander. So he was born in Kourou in 1934, went to the States for a while, and he came up with something pretty similar to the idea of the Schwarzschild solution that I said before, except it's rotating. So you can think of it something like this. You can see this line is twisting around. So a Kerr black hole is one that's rotating, and it's a more complicated solution than Schwarzschild's one, but it's much more realistic as well. And he returned to the Canterbury Maths Department in the 70s, and now I think is in Tauranga. So, all right. So the next part of my talk, I want to address where black holes come from. So effectively, I said in order to get to this point, you have to squish everything on the Earth and the Earth itself down to a golf ball. You clearly need a pretty extreme environment to be able to do that. So how does this happen in the universe? So probably many of you guys are pretty familiar with this. This is a picture of a few different stars. So Sun-like star is about this size. Red dwarfs are pretty tiny, but they're the most numerous in the galaxy. Lots of Sun-like stars around, but then there's a few of these really giant ones, blue dwarfs, and this here I got the graphic from a picture talking about the largest star that we know of, so they called it R136A1. This thing is like 240 solar masses. So these enormous stars burn incredibly brightly and very fast, and they only live a pretty short amount of time. So for a Sun-like star, or a smaller one, when they die, there's not all that much that happens. I mean, well, they do pretty interesting things. But basically, the stars are sitting around burning their hydrogen into helium in their cores. At some point, they use up all their hydrogen, or enough of it so it doesn't work anymore, and so they can't support their weight anymore, and so things start happening. So for our sun, what will eventually happen is that it will start burning the hydrogen into a couple of other elements and turn into a white dwarf in its center, which is a very compact star, but still way above black hole densities. But for these really big stars, blue dwarfs or these kind of super giant unstable things, they have so much gravity, and they use up all their heat as they burn, that they form a core collapse supernova, that just means the entire core of the star collapses downwards, and there's nothing to stop it until it reaches nuclear densities. So that's like the density of the nucleus of an atom, which is getting pretty close to black hole densities. So you have to imagine that effectively you've got the center of the star here, the core of it. At some point it runs out of fuel to burn at all, and so there's no heat pushing outwards. The whole thing just starts collapsing downwards, and there's nothing to stop it until it reaches down into the sort of densities of the nucleus. And if you get an even bigger one, it can collapse all the way down to a black hole. So effectively it's just gravity and nothing else causing this massive collapse, and this is how you manage to squeeze all that matter into a small enough space for the black hole. So as I said, this is a type 2 supernova, a core collapse supernova. So this is obviously an artist's impression. You've got an outer envelope, the core collapsing downwards, forming an enormous explosion in the process, and we now observe these pretty regularly, of course. So here's the Crab Nebula. Just to point out, this is the explosion that was 900 years ago, and we're observing the sort of the exploded bit with all this stuff. And then right here you've got a what's called a neutron star or a pulsar. So this is really this really high density object, and that's the center of this core collapse supernova. So this isn't a black hole, but if it were a somewhat bigger star, or maybe later once it collects a bit more matter, it would turn into a black hole. So as far as we know, this is the only way to, well, this is the only really well accepted way to form black holes in the universe, is from the collapse of massive stars. So there's two main types, or that we classify them into. Stellar mass, a kind of 3 to 30, although that's probably extended up to about 100 now. So called because of the mass of stars. And then supermassive black holes, which live in the center of galaxies, and they're larger than 1,000,000 times the mass of the sun. So basically we know now that effectively every single larger galaxy has a supermassive black hole in its center, so larger than 1,000,000 times the mass of the sun. And these things seem to be basically very important for the formation of galaxies in various ways. And so we have one in the Milky Way called Sagittarius A star, and I'll show you a picture of one in a bit, that one that I showed at the start. So it might seem a little bizarre to have this classification here with 3 to 30 and then more than 1,000,000. So what happens to all the ones in the middle? So as far as I know, we don't know of any black holes that are smaller than a few or a couple solar masses. And if we found one, this would be a big deal, because that mechanism that I talked about before for creating the black holes from stellar collapse sort of necessarily has to create one about the size of a star. If you were able to create one that was significantly smaller than that, it would tell us that we're missing some key physics of how black holes form. So we don't know anything about tiny black holes. As far as we know, 3 is kind of a lower limit. But the intermediate ones, so in between these two, these are ones we're starting to find now. So these certainly exist out in the universe. They've just seemed much less common than the supermassive ones and the stellar mass ones in the center of galaxies. So that's why this kind of funny classification with the supermassive and stellar mass and then nothing in between. But there's a few of these we know about now, and even LIGO is seeing some of these intermediate ones too. Okay. So the final part of that talk, I wanted to go through how we know that black holes exist, because it's all well and good to have these theories for what they do. If we can't actually test these through observations, then it's almost meaningless. So how do we actually see this? Particularly because they don't emit any light, because they're black, as I said before. So I want to go through 3 different ways. And you'll see the things on the side are showing that they won a Nobel Prize in physics pretty recently, so this has been quite a hot topic. So the first is to watch some nearby stars. You basically make a movie of things moving around and then say, well, they're moving in such a way that there's something incredibly dense and heavy right there. And the only thing we know about that could fit the bill is a black hole. And this won the Nobel Prize in 2020. The second way is to watch stuff falling in. So paradoxically, despite the fact that they're black, they're also the brightest things we know about because stuff falling in gets incredibly hot, and these are things like quasars and X-ray binaries and other things. And then finally, observe the ripples in space-time itself. So this is LIGO and Virgo and these other gravitational wave observatories that have been coming online just since 2015. So this final one is super exciting and like a very recent addition to astronomy, kind of a new way to look at the universe in the last few years. Okay, so what I'm going to show here is actually a movie of a simulated movie of the galactic center. So in the galactic center, we have a 4 million solar mass black hole called Sagittarius A star. And the main reason we know it's there is over the last 2 decades, people spent a long time mapping the trajectories of all the stars in the nearby region to show that there must be this very dense, heavy object there. So yeah, I think this movie should work. So it's going to kind of trace out the paths of various stars. And you can see just that by watching these, that there sort of has to be something here, which is very, very big and heavy, and we can't see it. At least not easily. You can sort of see it. So from that, you can work out the mass of this thing, or constrain the mass of this thing, and infer from there that it must be a black hole. So this is a different movie which is 2D instead, and it's the actual data, so it's not quite as cool an animation, but it's actually probably more useful. You can also see the time scale on the top here, on the top there. So, you know, this is a pretty painstaking movie to make over the course of many years. Zooming in here, if we look at the trajectory of some of these stars, particularly that one, you can see it does this, it's on a highly elliptical orbit, and you know, by constraining the distance to this object here and the fact that the other object didn't move, you can constrain its mass and infer that the only real thing it can be is a black hole. So that may be not a completely solid way of saying that black holes exist, but combined with the other two, it's going to be pretty good. So the second way is to watch stuff falling in, and as I said, it's going to get really hot. So remember, even to get out of the Earth's gravity, we needed a nuclear explosion, basically, because you have to go 11 kilometers a second. That's why it's so hard to launch a rocket as well. So we needed that. So what that also means, as a kind of converse, is that if you fall inwards, by the time you get close to the black hole, or any object really, you're going incredibly fast. And that means if you crash into other stuff when you're going incredibly fast, you get incredibly hot. So by the time you reach near to the event horizon of a black hole, you've heated up enormously, and then you radiate lots and lots of energy, so these sources can be incredibly bright. If you have significant amounts of matter falling into a black hole, they can be some of the brightest things we know about. So one way to quantify the sort of effective brightness of an object is through E equals mc squared. So Einstein's other really famous equation says that energy is proportional to the mass, with the proportionality factor being c squared, which is a really big number. So tiny amounts of mass convert into enormous amounts of energy through this equation. So any process you can think of that releases energy necessarily also changes the mass of its constituents a little bit. So like a chemical reaction, burning coal or something, the mass of the constituents will be 0.00003% lighter than the reactants that went into it in the first place. And that difference in mass is converted into energy. So any chemical reaction is converting about that much mass into energy. Basically energy, anything we can think of on Earth. Nuclear stuff is of course much more efficient. So nuclear fission, like a power plant, will convert about 0.1% of the mass into energy, so 1/1000th. Nuclear fusion, like a hydrogen bomb or the sun, will convert about 1% of the mass into energy. So significantly more efficient, but still doesn't sound amazing. If you fall into a black hole, you can convert 40% of your mass into energy. So this is an insane amount of energy that comes off from even a tiny bit of mass. So as an example, to kind of put this in perspective, the largest nuclear bomb that humans have ever tested was the Tsar bomber in Russia in the early 50s. And this was like this horrible 50 megaton monstrosity, which flattened half Siberia. You would get about the same energy release from dropping 5 or 10 kilos into a black hole. So the amounts of, if you imagine then dropping a star in, you can see the amount of energy that comes out is, well, astronomical. So we first kind of started realizing that this was happening in the 60s. There was this guy, Martin Schmidt, who was an astronomer, who found these things that they called quasi-stellar object, or we now know them as quasars, and there's various other related versions of these. Effectively, he saw these things, they thought they were stars, but he measured their redshift, so how fast they were moving away from us, and found it was really fast, which says that they're really far away. And in order to be as bright as they are and be that far away, they must be, in order to look as bright as they are and be that far away, they must be incredibly bright naturally, way brighter than anything we've imagined. So actually the quasars can often outshine their entire host galaxy, so all of the stars in the galaxy by a factor of a few thousand. So the stuff falling into the black hole is a few thousand times brighter than, you know, a few 100 billion stars. So that gives you an idea of the kind of power we're talking about. The picture you want to have is something like this. You've got a black hole. As it falls in, it forms a pancake structure because the angular momentum of the stuff falling in is conserved. So you get like this disk, and then as it falls in, it gets hotter and hotter and hotter, it gets really bright, and usually shoots out these jets down the side as well. Temperatures to 10 billion degrees, and normal matter can't handle this at all, so everything becomes plasma. So this is kind of the stuff I study. So this has become, this process of watching stuff falling in has become quite exciting recently with the Event Horizon Telescope, which is a collaboration, and they released their first image in 2019, which is our first picture of an actual black hole. So they took a picture of M87, giant elliptical galaxy in Virgo. This is its picture up here. Oh, it's not there. And we've known for a long time about these big radio jets coming off it, which have like highly relativistic, incredibly hot plasma shooting out way into space. But they took this image here. I should say, the black hole is 6.5 billion solar masses, so it's about 1,000 times heavier than the one in our galaxy. That's why they chose this one, it's because it's really heavy, so it's bigger. So this is the image they took of this black hole, and this is right in the center. So this here is the actual event horizon. So this hole in the middle that you're looking at is the actual black hole. That's the black hole itself. And then the bright stuff around it is the stuff that's falling into it as it goes. So they image this in the microwaves, not in the visible. But because this thing is so far away, they had to have an insane resolution to be able to see this. It's like 60 microarc seconds, which is like looking at a hair, like a human hair, edge on in Wellington. And to do that, they had to build a telescope the size of the entire Earth to not have the diffraction limit. And so to do that, they joined together a bunch of different radio telescopes interferometrically, processed the data for like 2 years, and then finally came up with this image. So it's a really amazing achievement. This is our solar system to scale, so that's the orbit of Pluto. So this is a truly massive black hole because, our solar system would easily fit inside its event horizon. But it does weigh 6.5 billion times the mass of the sun. So, yeah. So that's the picture. It's a bit fuzzy, as you can tell. This is a computer simulation of the type of thing we're looking at with that. It's not the actual one. People have done simulations of the actual one, but this is the type of thing we're seeing here. So it looks a bit funny. I said before it was like a disc shape, like a pancake, but here it looks kind of lopsided on top. So the reason for that is actually because a round black hole light doesn't go in straight lines anymore. So this stuff on top here, what we're actually looking at is the back of the black hole, and light is coming from the back, curving around and then towards your eye. So you see this as a stuff on top of the black hole, That there is from behind it, but it's actually a normal pancake shape. And then there's some weirder stuff, like this can be caused by light going around in circles, several times even around the black hole, because it does that because the space-time is so curved. And then the fact that it's brighter on this side than that side is because the matter is rotating around, and also because the black hole is rotating. It's one of these Kerr black holes rather than the non-rotating black hole. Okay, so that was what I wanted to say about stuff falling in. Basically, gets really hot and therefore really bright. The final way is probably the most exciting, and it sounds like a bunch of people in this room are pretty familiar with it, and that's to actually watch the ripples in space-time itself. So gravitational waves, which are a prediction of general relativity and are caused when two black holes collide. So imagine two black holes orbiting each other. This is a really strong perturbation, and it wobbles space-time back and forth, and that waves out into space. So this here is a simulation, computer simulation of what it would look like to you if you were watching two black holes with stars behind them as they spiraled around each other and in. And the weird shapes are caused by all those effects I talked about before. So it's light going in funny curved directions. So this is just a movie. All this stuff is caused by the weird shapes, the light going around in circles and stuff. And you can see that the black holes are slowly getting closer together. And as they do so, they're speeding up because their orbital distance is getting slower. It is getting closer. And then once they touch, the two black holes touch, they turn into one. So that's a prediction of relativity, is that you can't have two event horizons touching without it becoming just one black hole instead. So you basically make a big black hole from two small ones. So I want to play the video again. I think it's on loop. But this time, rather than looking at the black hole itself, look in the corner, like over here instead. And you can see the stars wobbling back and forth like this. That's you seeing the gravitational waves go by, effectively.
It's the neat skies sometimes.
Yeah, hopefully it's not the atmosphere. So as this happens, as the two black holes collide and merge, they also release a lot of gravitational waves which fire out into the universe, and you can see these. So LIGO effectively just watches these ripples go by. You imagine two black holes colliding over here, a billion light years away, and they propagate past us, and then we measure this. So this is an incredibly impressive technical achievement to be able to do this, because so what they do is they have two big lasers pointing at right angles, and they can measure the change in distance between these two things incredibly accurately. So they can measure changes in distance of 10 to minus 18 meters, which is like 10 to 100 million times smaller than the radius of an atom. So it's kind of unimaginable that this is even possible. There were two when they first started, both in the States. Now there's one in Italy called Virgo, and a new one in Japan. So you're effectively just imagining an incredibly sensitive microphone that they've built that can measure these wobbles in space-time as they go by. And by measuring the wobbles in space-time, they can infer the properties of the actual black holes that collided as well. So this is going to be a video of the first event they found in 2015. And by looking at the shape of the wobbles, they know that it was a 36 solar mass black hole colliding with a 29 solar mass black hole. And in the process, it released 3 solar masses just into pure energy that was the gravitational waves flying off into space. So a lot of energy involved. The other cool thing about this is the actual speed they're rotating around is at like audio frequencies. So you can listen to it, and it's what it would actually sound like if you were standing near the black hole and could hear it in the audio. So this is a picture of that, if you can hear it. So the little like whoop sound, that's the two black holes as they spiral really close and then collide. So the movie I showed before, where they were kind of going slowly and then went like that was way slowed down. These 30 solar mass objects are actually orbiting each other like 100 times a second, which is pretty hard to imagine. So as I said, it's a very exciting time in this area now because that was one in 2015. We've now got like 40 of these or something. Not sure exactly. This picture was from 2020 and they keep finding more, so it's hard to keep up. Basically what this picture shows is mass on this axis, and then the two dots are two that have merged to create a bigger one. So the biggest one they've found now is two that have merged to create a nearly 160 solar mass black hole, but there's all sorts. And the really cool thing about this is you can start doing all the statistics that you would usually do with stars, but now with black holes instead. And we're seeing the universe in a completely different way. This isn't like some different form of light. It's completely different. So it's a very exciting time to be able to see the universe in another way. Also amazing that it was predicted by Einstein 100 years ago and then observed now with technology that would have been completely unimaginable to him. So, quick recap: the ways we know black holes are there, and put together these three things of very good evidence that these guys actually exist. So, first way, you just watch some nearby stars. It's basically like making a movie of the galactic center. We have to do it in our galaxy because other ones are too far away, so you can't resolve it. Watch stuff falling in. So this you can see. There's quasars where you watch the matter falling into the black hole are some of the furthest away objects that we know about, like redshifts, coming from only a few hundred million years after the start of the universe, because they're so bright we can see them so far away. And then third, we have this new way of looking at the universe in gravitational waves with LIGO and Virgo, which is already yielding heaps of interesting insights. So I guess I wanted to finish up by just outlining a few of the mysteries that still surround black holes. So the biggest one is what I said at the start, that this is actually like the one object that we really know of that physics cannot describe. We can't describe the singularity at the center. We have no theory that can possibly be used to predict its properties. And so that's just a big mystery, obviously. And then there's a lot of people trying to work on this merging of quantum mechanics and gravity, which is sort of the big problem in physics at the moment, by thinking about what black holes do. So things like the black hole information paradox, if you've heard of that, and other things that you can use as thought experiments to try and understand how you might manage to merge these two together. On a kind of slightly less crazy front, things like LIGO, they're now able to actually test some of the really intense predictions of general relativity, which they couldn't before. So for instance, by matching those waveforms, they can see if general relativity is matched perfectly or if there are slight deviations. And if there were slight deviations, this would be a really big change in our understanding of physics. But so far, there haven't been. So far, it seems like general relativity works perfectly, but that's kind of an ongoing research. And then the types of things I do, which is like studying how matter falls in and how it heats up and how it cools down from radiation and that kind of thing. So I guess the main point I wanted to get across was that they're not like some, crazy thing which is not well accepted or something. There's a lot of people in physics and astronomy now studying black holes, and they're a pretty interesting thing to think about when you look up at the universe. So yeah, thanks.
All right. It's weird to speak to a microphone that we think doesn't work, but this is for the people that are watching the live stream. If there are any questions, I can pass on the microphone and we can ask a few questions. Is that all right?
Yeah.
I actually have a question.
Sure.
I'll start up. It's amazing. I mean, I think I'm going to have to watch the talk again just to get all the details, because there's a lot there that I have to really think about to understand. At a very basic level, we usually speak about what you've said, how really big stars can end causing a black hole when they die. And personally, I often refer to Betelgeuse or Antares as being really huge stars, but not big enough to make a black hole. And then I usually get the question, so how big does the star need to be? And I think you've mentioned it, but can you repeat if so?
Oh.
How big, how small,
So
what's the smallest star that can make a black hole?
So we don't really know the answer to that question, but we know the the smallest star that makes a core collapse supernova. So that would be about 10 times the mass of the sun.
Only.
Yeah, but that will make a neutron star instead of a black hole. So effectively, you've got this process where imagine it eating up all its fuel in the center, and if it eats it up fast enough, it gets to iron, and then it collapses, and that's the core collapse. So 10 solar masses is approximately the limit to make that. Then once it collapses, you get the neutron star in the middle, and you would expect that a bigger star makes a bigger thing in the middle, which is true. So at some point, the star gets big enough that it probably, it gets really complicated and we don't really know, but probably what happens is it makes like a very highly energetic, rotating, very hot thing that then will collapse into a black hole afterwards. And that probably happens more like 30 solar masses or something like this. So we don't really know, but probably 30 solar masses.
But that's Antares.
Yeah.
Wow. So it could happen that Antares turns to a black hole. We just don't know how.
Yeah, guess so. Yep.
Okay.
And then there are ideas from like the early universe, really like the first generation of stars. Maybe you had these massive collapsing things that collapsed into 1,000 solar mass black hole. But the models to understand like neutron star and black hole formation in detail from supernova is actually really difficult, and we don't really understand it in detail quite yet. But around 30.
Yeah. Thank you. Mike.
Oh, thanks for the very interesting talk, Jono. I was wanting to know how do the supermassive black holes form?
Yeah, that's a great question, and also we don't really know the answer to that. So what I said from LIGO is basically the answer. If a black hole eats something else, it just becomes a bigger black hole. So, a star can't like eat something else and then just, I guess it sort of can, but it doesn't really happen. But if stuff falls into a black hole, like matter falls in one of the disks in a quasar, it just becomes a bigger and bigger and bigger black hole. So the more stuff that falls in, the bigger it becomes. So what you need is some seed to start it all off. And then it will, if it keeps accreting matter, if stuff keeps falling into it, it just gets bigger and bigger. So you need a sufficient gas supply. So people think that you start out with some reasonably sized seed, maybe 1,000 solar masses, and then in the process of galaxy formation, you have lots of stuff falling in, and it just makes it bigger and bigger. And so you get this relationship, like bigger galaxies have bigger black holes, basically. There's a relationship between the size of the black hole and the size of the galaxy. So they form together from matter falling in, effectively. Does that answer the question?
Hi. So what's the closest black hole to us? You mentioned Sagittarius A. Is that the center of the galaxy?
That's the center of the galaxy, yeah. It won't be the closest one. I don't actually know what the closest one is. We probably don't either. Oh, no. Well, I hope probably not. If there was, it would probably be tiny, and if we found it, it would like revolutionize everything we know about black holes. So very unlikely to be one in our solar system. If I had to guess, I'd say around 1,000 parsecs away, but I don't really know. If someone else knows, feel free. I'm not sure. But there are lots in the galaxy that are stellar mass black holes that we do know of. So stellar mass black holes can be really bright when they're in a binary system with another star, often a blue supergiant, which is feeding them matter, and so you get these X-ray binaries, which are really bright X-ray sources. And so there's quite a few of those in the galaxy. So there's a bunch around, yeah.
What happens to those once you suck the guts out of? What happens to those stars once they suck the guts out of the parent?
All right, well, so,
They'll cause most of them around blue supergiants. And then that supergiant, once it loses so much mass, it will supernova.
Yeah, it depends. And I think a lot of different things can happen, but you can get a supernova going off when it's in a binary with a black hole. That's one possibility, or maybe it doesn't. It depends on the mass of the black hole, the binary, and like the evolution of stars in binary systems is one of these problems in astrophysics, which is notoriously difficult and not very well understood at the moment. And I think there are lots of different things that can happen. Yeah.
Yeah, I watched a really stupid movie once, probably called The Black Hole or something, where scientists managed to create a black hole on Earth. That's never going to happen, is it?
Not with any current technology, but you can make a case that it would be a pretty exciting thing to have. If you could make one, you could do an awful lot of interesting science with it. Well, you just need a lot of, you need to concentrate a lot of energy in very, very small space. So the only real proposals, I think, involve having a lot of lasers, gamma ray lasers, all pointed down at one very small point. And if you can get enough energy in there, you'll in principle form a black hole.
Don't tell anybody that.
It's not easy. I wouldn't worry about it.
The important thing is you don't need mass, you just need density.
Exactly. Yeah, you can make it, a black hole can be any mass. Yeah.
You can have a 1 gram black hole.
You can.
Which isn't going to cause anybody any grief at all.
Well, actually it will. But.
1 gram.
Yeah, but that's right. In principle, black holes can be any mass. So if we created one, it wouldn't be 2 solar masses. It would be quite a small one. And a smaller black hole just has a smaller radius. So
the event horizon would have to be within the test tube.
yeah, it would be very, very, very small.
So it's not going to start sucking in all that.
The
No,
test
well,
tube.
stuff would orbit in the same way that it would
is
for
amazing.
any other.
Hang on,
mass.
I'll pass the mic to Mike.
One thing about very small black holes is, doesn't Hawking predict though that
Yeah.
black holes evaporate, and as they evaporate, they get faster and faster as they get smaller.
Exactly.
So it's very you managed to make a very small black hole, isn't it going just to disappear almost as quickly?
It is very good point. Yeah. So the smaller. So to explain to other people, there's this thing called Hawking radiation, which some of you might have heard of, which is a very small amount of radiation that comes out of the surface of a black hole from particles getting created on either side of the event horizon. And the prediction of Hawking radiation is that the smaller the black hole, the faster it evaporates because of this radiation, and the brighter the object is. So actually, once you make a black hole really small, it becomes really bright because of this Hawking radiation, and it also evaporates in a very short amount of time. So you actually have to be pretty careful if you're making like a black hole the mass of a car or something. It will evaporate quite quickly and create an enormous explosion in the process. Because of this Hawking radiation. But I should also say Hawking radiation it's not been observed. I mean, our current theories predict it, but it's still theoretical. And we have no real hope of observing it right now.
Thank you. Any more questions? Oh, there is an online question. I would imagine a model of a black hole is quite complex. What kind of computing power is needed to model black holes? Do you need a supercomputer?
Yeah, I mean, that's a great question. I guess it depends what you need to do. So the video, like I showed this thing, these are run by basically programming in those equations of general relativity that I showed before into the computer, and then evolving it in space-time to watch what happens. And that is quite difficult. You need a supercomputer to do so in a reasonably good way, and it's something we've only been able to do quite recently, figure out how to actually do this. If you're just looking at an isolated black hole and something else, then it may not be all that complicated. But once you have stuff colliding and no symmetry or anything else, it becomes pretty difficult to do. Yeah.
Awesome. Thank you. Any more questions? No? If you're watching online and you have questions, you can always type them and we will email them to you.
Sure.
It's been an amazing talk, so thank you so much. We still have one more talk to go this year in November, and then December will be our annual Starbecue. So come along. I believe it's the first time visiting the observatory. So before you go, you need to see the actual telescope.
Yeah.
And hopefully we can see you again.
Yeah, I hope so.
One big round of applause, please. Thank you.